All right, everybody. I know you're all excited. This is the very last set of notes that we need to do for this year in chemistry. So we're going to finish off chapter 19 here, and that'll be it. So let's get into this. The last thing that we need to talk about in this chapter about acids and bases is putting acids and bases together. You know, up till now we've been talking about an acid or a base, but really we haven't been talking about them together. So usually what we'll do is we'll put an acid with water or put a base with water, but we won't put it with another acid or base. So that's what we're going to start talking about here, is mixing them together. Right? Acid-base reactions. An acid-base reaction is also called a neutralization reaction because the acid and the base are going to neutralize each other, as you're going to see here in a minute. When acids and bases react, they always form some kind of salt. And if you remember, several times this year we've talked about the fact that in chemistry, salt doesn't just mean the stuff you shake on your French fries. Salt is any ionic compound. So acids and bases react to form some kind of ionic compound, a salt, and water. Okay. So again, let's look at an example of this. So you can see in the example here, we started off with some hydrochloric acid, some HCl, and we added some magnesium hydroxide, MgOH2. And then we essentially are doing a double replacement reaction, right? Where they're switching partners. If you remember your reactions from a while back. So the H and the OH are now going to go together, and the Mg's and the Cl's are now going to go together. Right? And on the other side, we get NgCl2. That's our salt. That's our ionic compound. And we get H2O. There's our water. Okay, because the H's and OH's go together to make it water. And the Mg's and Cl's, we have to use our charges and do crisscross to figure out that it's MgCl2. And of course, I've already balanced this. Now, if we were to take the acid and the base and the salt, which are all aqueous, and we were to split them, dissociate them. If you remember, when we did a double replacement reaction a few chapters back, we said double replacement reactions that include aqueous species, they have to be dissociated. We're going to write out a net ionic equation from this. So let's do that. Let's take the HCl, the MgOH2, and the MgCl2 and actually split them. Because remember, when those are actually in water, aqueous, that means that they are split. They are separated from each other. So the HCl is the H positives and Cl negatives. The MgOH2 would be the Mg2 positives and the OH negatives. The MgCl2 would be the Mg2 positives and the Cl negatives. And of course, then we have water. Water is just water. It's not ionic, so we don't split it. And so there's the full ionic equation. And then we said every time we write a full ionic equation out, we should see some spectator ions, right? Some ions that are the same on both sides that we can cancel. So of course with this we can see that the Mg2 positives are going to cancel because they're the same on both sides. And so are the Cl negatives. So the Cl negatives and the Mg2 positives are our spectator ions. They didn't actually do anything in this reaction. They didn't change at all. So we're just going to separate them. We get rid of those and we're left with net ionic equation, which is what's left over. So we're left with the H positives, the OH negatives, and the water. Right? They were all 2s, so I just took the 2s out. And so we're left with H positive plus OH negative makes water. Well, what's the pH of water? Right? We said before, pH of water is just neutral. It's 7. So if H2O is what our main product is here, and H2O is neutral, then we just neutralized the acid and the base. So that's why we call this a neutralization reaction, okay? Because when you put acids and bases together in exactly the right amounts, right? Remember, a balanced equation assumes that we're taking exactly the amount of acid and exactly the amount of base that we need to react them fully together. Then we would only get some kind of salt and water. And water is neutral, so it's a neutralization reaction. Now, anytime that we have a balanced equation, we can do some stoichiometry. And again, don't freak out. Stoichiometry is just the stuff of moles and grams and liters, right? So we can do a stoichiometry problem with any acid-base reaction just like we would do with any other reaction. So let's just take a moment and do an example of this. I know it's a little bit of review. It's good. So we go back and kind of review about how to do a stoichiometry type of problem, but we're going to do it with an acid-base reaction. So this says how many moles of potassium hydroxide are needed to neutralize 1.56 moles of phosphoric acid. Now, if we're going to do any kind of problem like this, we need a balanced equation. Now, it didn't tell us a balanced equation, but they told us enough that we can figure it out. Okay, so let's take a moment here and try to figure out what this would be. So potassium hydroxide is one of the reactants. So we know that potassium is K. It's in the first group on the periodic table, so it's +1. Hydroxide, we've memorized by now, is OH with a -1 charge. So if you take those two and you put them together, you would get just KOH, right? Okay, so there's potassium hydroxide. And it says it's going to neutralize phosphoric acid. So phosphoric acid must be the other reactant. So acid rules. Again, we have to remember back. I know it's going back a ways, but we have to remember back how acids work. If you have the name of an acid and it ends in ic, but it doesn't start with hydro, then the original ending of the ion in this acid was ate, right? So that means that phosphoric acid has phosphate in it. So phosphate we know is PO4 with a -3 charge. And then being an acid, it has to start with H. And we know that H's are always +1. So we're putting H +1 with PO4 -3. Well, we're going to crisscross, so that means that we need 3 H's, right? So we have H3, but H is +1, so that means we only need 1 PO4. So it's H3PO4. Okay, so we know what the reactants are in this reaction. It's KOH plus H3PO4. Now we're going to figure out what the products are going to be. Now it says above on this slide, it says that a neutralization reaction is an acid and base react in aqueous solution to form a salt and water. Well, let's do the easy part first. So I know one of my products is going to be water. So that takes care of the H's and the OH's. So the H's and the OH's react to form water. So the other two ions that are there are going to be my salt. So that would include the K's and the PO4's. Now again, we have to use charges to figure out what the actual formula would be when you put K and PO4 together. So it's K +1 and PO4 -3. So crisscrossing tells us how we need 3 K's and just 1 PO4. All right, so there's our equation. KOH plus H3PO4 yields H2O plus K3PO4. Now we have to balance this out, right? So if I were to balance this using the K's, I would need 3 K's over here. And then if I were to balance out the P's are balanced out all right. And then when I balance out the H's, so I have 6 H's on the left, and I have only 2 on the right, so I would need 3 here to make 6 H's on the right. And then finally, we look at the O's. On the left-hand side, I have a total of 7 O's. On the right side, I now have 7 O's. So there it is. There's the balanced equation. Once we have a balanced equation, now we can solve this problem. And by the way, this problem is relatively simple because it's just a mole-to-mole problem. We're not working with grams or liters or molecules or anything else. We're just working with moles. So this actually turns out to be a relatively simple problem once we have a balanced equation. So we start with our given. So it says that we have 1.56 moles of phosphoric acid. So that's H3PO4. Right? And it wants to know how many moles of potassium hydroxide are needed. So the end of this problem should end with moles of potassium hydroxide, KOH. So we have to put the units on the bottom. So the units on the bottom of our conversion factor have to always match the units that are at the beginning in the given. So that means that moles of H3PO4 would be on the bottom as our unit because it matches the moles of H3PO4 that we started with. And then the unit that we put on the top is what we're trying to go to, which is moles of KOH. Now, we're doing mole to mole. That's a mole to mole ratio. Mole to mole ratios come from the balanced equation. So how many KOHs in the balanced equation? Well, there were 3. Right? How many H3PO4s were there in the balanced equation? There was only 1. So there was 1 here, there was 3 here. And so in the end, this is telling us that if we took 1.56 times 3, we would get our answer. And again, you should be doing that on your calculator. While you're doing that on your calculator, I'm going to erase this and put up the nice, neat version that I've already typed in. So there we go. Final answer would be 4.68 moles of KOH. Okay. We have 3 sig figs, by the way, that we started with, so we ended up with 3 sig figs in our answer, so that's good. And so there's a really simple way of doing stoichiometry with an acid-base reaction. To tell you the truth, we could have done this same problem back 5 or 6 chapters ago in our stoichiometry chapter, and we would have known how to do it then too. So this was a good review of, the type of problems you should be able to solve by now. Now that whole idea of taking an acid and a base and reacting them together to get a pH of 7 is actually really powerful because it allows us to actually figure out things in real life that we wouldn't be able to figure out before. And we're going to use a process called a titration to help us do this. So a titration is a method of using a solution with a known concentration to find the unknown concentration of another solution. So in other words, we're going to mix 2 solutions together. We know what they are, but we don't necessarily know one of the concentrations of one of the reactants. But we know the concentration of the other one. And the great thing is, if we're talking about acids and bases, we know that if we put just the right amount of acid and base together, we should end up with a pH of 7, right? So the idea is that if we know the molarity of one of those acids and bases, then we can figure out the molarity of the other one because we know when they're going to be equal. We just have to look for a pH of 7. So here's the equation we're going to use, and I hope that the equation looks a little bit familiar to you, right? MV equals MV. MV equals MV is the same kind of equation that we used when we did dilutions back in chapter 16. So MV equals MV, but this time the M and the V are going to be used for the acids and the bases. So the left-hand side of this equation is for the acid. The right-hand side of the equation is for the base. Now, I want to make something clear here. Notice I didn't say MA for acid, I said MH positive and VH positive and MOH negative and VOH negative. And the reason I did that is because I want you to realize that when we talk about the molarity of an acid, we're talking about how many H positives there are. Let's say, for instance, we were talking about phosphoric acid from the problem right before this. Phosphoric acid was H3PO4. There's 3 H's in H3PO4. So when we talk about the molarity of the acid, we're actually talking about the molarity of the H positives that you get from the acid. Okay? So we're going to go back to this balanced equation from earlier. We're going to use this as our example to help solve a titration type problem. So here's my problem. I know that I have some hydrochloric acid that is 2 molar, but I'm going to react it with MgOH2, which I don't know the molarity of. That's my base. I have 25 milliliters of HCl, and it takes 30 milliliters of MgOH2 to actually neutralize it, to get to pH of 7. So if I have 25 milliliters of a 2 molar solution of HCl, and I react it with 30 milliliters of an unknown concentration of MgOH2, I get to a pH of 7. Now, if I do that, that means that I should know what the molarity of H positives is. I should know what the volume of the H positives is, because that's my acid side. I know the volume of the OH negatives, that's the 30 milliliters, but I don't know what the molarity is. And so I have one thing that I don't know out of the 4, so I'm going to plug in some numbers here. By the way, don't forget this is net ionic equation would just simply be H positives and OH negatives. Doesn't matter how many Mg's or Cl's we have. No, they don't do anything. Okay, so let's take that equation from before and let's put in the numbers now. So the molarity of the H positives is 2 molar. The volume is 25 milliliters. The molarity of the OH negatives, I don't know, so I'm going to leave it as MOH negative. And then the volume is 30 milliliters. So to solve to get MgOH negative by itself, to isolate the MgOH negative, I would have to multiply 2 by 25, so that gives you 50. And then I'd have to divide it by 30, right? So I would end up getting an answer of 1.67 molar OH negatives. Now, here's the issue. This is the molarity of the OH negatives. But this wants to know what's the molarity of MgOH2. Now, MgOH2 has 2 OHs in it. So we're going to have to divide this number by 2 to get our actual answer. If this was MgOH1, we would have been done, right? The 1.67 molar would have been our answer. But since there were 2 in there, I had to divide by 2. So again, occasionally this happens, and so that's why I picked this out as our example problem, because I think it's good for you to see what happens if you have more than one OH or more than one H in your acid or your base. Okay? So again, a titration problem is relatively simple because we're simply using the MV equals MV equation. We know that if we have so much acid, we have to take so much base to react it together. Now let me give you a little preview of how a titration actually works in the lab. What we would have been doing in a lab if we were at school, this would have been a multi-day big thing that we would have done. Unfortunately, we can't, so I'll probably have some kind of online simulation of it that you'll be working with here a little bit later. But here's the general idea of how this works, okay? So we're going to have a burette. Burette's sort of like an upside down graduated cylinder, but it's got a valve at the bottom. right? And so if we were to put in some acid into like an Erlenmeyer flask that you see there, and we were to put some base in the burette, and we were able to add a little bit of base to the acid at a time, little bit, little bit, little bit, little bit, eventually we would get to the point where the acid and the base are equal to each other, and they neutralize each other and become a pH of 7. Now, how do we know when we get to a pH of 7? Well, we would either have to have a pH meter that's in the Erlenmeyer flask the whole time so we can see what the pH is, or we would have to have some kind of acid-base indicator. We talked about acid-base indicators a couple times ago. So an indicator is one of those substances that changes color based on the pH. So the indicator we would have used in our lab in class is an indicator called phenolphthalein, right? So phenolphthalein is colorless when it's an acid, and it's pink when it's in a base. So that means right around a pH of 7, the actual color would start to turn from colorless to this dark pink color. So how do we know when we would reach neutralization, a pH of 7? Just as the color would turn into that pink color, we would stop adding base, and we would measure how much base had we added up to that point. So we would know volume of base, we would know volume of acid, and then we would either know the molarity of the base or the molarity of the acid. One of the two we would know, and we could calculate the other one. Okay. If the acid and the base are both strong, right, and we were to graph how this would go. So you notice that I have pH on the y-axis here, and I have the milliliters, the volume of the NaOH. So that's my strong base in this case. So if I had a strong acid like, let's say, HCl, hydrochloric acid, and I started adding NaOH to it, well, at first, there's going to be a way more acid than base. And so the pH stays really low at first. So you notice in this graph that the pH line there stays down by 1 or 2 almost the whole way. But eventually, I'm going to start adding so much base that eventually the base is going to overwhelm all of the acid that's there and is going to neutralize all of it. And you notice that eventually the pH shoots up. And right in the middle of that is what we call the equivalence point. The equivalence point is when the moles of acid are equal to the moles of base, right? That's what the equivalence point means. And the equivalence point would turn out to be at pH of 7, because right at that moment, all of the acid and all of the base would have reacted with each other, and you would have just gotten a salt and water. And water is neutral, and you get a pH of 7. Okay? So the equivalence point occurs at a pH of 7 for a strong acid and a strong base. But a weak acid and a strong base, a little bit different, right? Look what happens in a weak acid strong base. A weak acid, first of all, usually doesn't start off at such a low pH because it doesn't have as many H positives. Right? So you notice that its line starts like around 3, but it does stay still pretty low most of the way until eventually the base overwhelms it again. But notice where the equivalence point is this time. It's not at a pH of 7 anymore. The equivalence point occurs to a pH of 8.5 to 9. So the equivalence point ends up being a little bit higher when you take a weak acid and a strong base and you react them together. These are called titration curves, by the way. Right? So we're doing a titration. We're taking an acid and a base, we're reacting them together. We're trying to figure out where they're equal to each other. So the equivalence point for a weak acid strong base occurs at a pH that's greater than 7. And of course, I don't have it on here, but I bet you could guess. If I were to take a strong acid and a weak base, and I were to titrate them together, what would the equivalence point be? Yes, it would be less than 7. Okay? The strong acid would end up dragging that equivalence point down further from the weak base. Okay, so the idea of a titration is, again, taking an acid and a base, reacting them together, and looking for where they're equal to each other so that we can solve for how much of one we had. We'll do a little bit more practice with that in the lab that we're going to do. And then, again, eventually you can get to your test. All right, so the very last part of this chapter then goes through and takes this idea of the salt that you would produce in that solution and says, are there times when that salt actually does matter? Are there times when the spectator ions of that salt actually do matter in this situation? And yeah, there are times when the salt actually does matter. It does actually affect the pH. And you don't get a pH of just 7. So if you take a salt and you dissolve it in water, right, it dissociates. The anions of the salt, the anions, right, would be the conjugate bases, and the cations of the salt, the positives, would be the conjugate acids, okay? And so what if you produce a salt that has a conjugate acid or a conjugate base in it that came from something that was weak? Well, we learned earlier that weak acids and bases produce relatively strong conjugate acids and bases. For example, say I take KF. So KF is potassium fluoride. Potassium fluoride is a salt. It's made up of potassium ions and fluoride ions, and at first it looks like any other salt. Like, why would that affect the pH? But I want you to think about where the K positive and the F negative would have originally come from, right? The K positive would have originally come from KOH, right? So the K here would have come from a base, KOH. And if you remember your strong acids and bases, KOH is one of our strong bases, right? So KOH is a strong base. So the conjugate of KOH is K positive. And if KOH were a strong base, then the conjugate acid of KOH is a weak acid. So this is a weak acid. Okay. In fact, it would be really, really weak. Therefore, it's not going to do anything in this reaction. It's not going to affect the pH at all. But the F here would have originally come from an acid, and acids always start with H, so I can assume the acid was HF. Now, if you think back to your 6 strong acids, is HF strong? No, it's not one of the 6 strong, so it must be weak. So if this were a weak acid, then its conjugate would be relatively strong base. Well, now F negative turns out to be something that we actually have to keep track of. It's not something that we can just completely ignore and just cancel out and say it has no effect on this reaction, because it's relatively strong. And that means that it's going to affect the pH. How would it affect the pH? Well, if you take, excuse me, if you take F negative and you put it into water, F negative being a strong base is going to attract H positive. It's going to accept H positives from the water, and it's going to start to form OH negatives in the water. And anytime you have OH negatives, you are now affecting the pH, right? So F negative causes the water to become more basic because it starts to form OH negatives. And that's important to note. The K positive didn't do anything. It was too weak because it came from something that was strong. In fact, let's label that up here real quick. So this was a strong base. That's why we got the weak acid. And this was a weak acid, so that's why we got a strong base. And anytime there's one part of a salt that is strong conjugate, that's going to affect the pH. Okay? So if you put KF, if you just take some potassium fluoride and you put it into water, you think, well, it's just salt in water. It's going to be pH of 7. It won't be, because the F will cause the solution, the water, to become more basic. Right? There'll be some OH negatives in there that weren't there before, and therefore KF is a basic salt solution. Now let's take another example. So you have some ammonium chloride, NH4Cl. If you put ammonium chloride in water, it will dissolve, it will dissociate into its two ions, NH4 positive and Cl negative. Now we have to think about where those came from. So NH4 positive is a conjugate acid, because it's got an extra H to it that it could donate. So that means it must have come from a base. So what's the original base of NH4 positive? It would have been NH3. So the NH4 comes from NH3. So NH3, is that a strong base or a weak base? Well, is it one of the 6 strong bases that we had to memorize? No. So this must be a weak base. And if NH3 is a weak base, that means that NH4 positive must be a relatively strong conjugate acid. Now the Cl must have come from HCl. And of course we know HCl is a strong acid, really strong acid. And that means that Cl negative must be a really weak base. And so we don't care about it. It doesn't do anything. It is truly a spectator ion. It does nothing. But the NH4 positive is a relatively strong acid. If you put it in water, it's going to want to donate some of its H positives away. Therefore, you're going to cause the water to turn into H3O positive, right? And that means that the NH4Cl, when you dissolve it in water, makes the water acidic. So it's an acidic salt. So salts, right? Salts of any kind, any ionic compound, could make water acidic or basic depending on what conjugates are in the salt. And it's a process of working backwards. You look at that salt, you think about what acids and bases it must have come from originally, and then that gives you an idea of what kind of strength the conjugate acid and base would have. Now, it's certainly possible that you can have a salt that has no effect on the pH. For example, the most famous salt of all, NaCl, comes from NaOH, which is a strong base, which means that Na would be a weak acid. And the Cl comes from HCl, which is a strong acid. Therefore, Cl is a weak base. So this salt is actually made up of 2 weak conjugates. So NaCl doesn't affect the pH of anything. This would cause the pH to simply be at 7. That's it. But not things like KF or NH4Cl. All right, let's try another one. Would a sodium acetate solution be acidic or basic? Now, several things you'd have to do. First of all, you'd have to know what's the formula of sodium acetate to begin with. So let's write that out. You know, sodium is Na positive. Acetate, remember acetate? It's one of those ions you had to memorize. C2H3O2 negative. Or if you really wanted to, you can memorize it as CH3COO negative. Either way, it doesn't matter. So if you put those two together, right, you would get NaC2H3O2. So there's your sodium acetate. But we want to figure out whether it's acidic or basic. So really the important part here is, where did the Na positive come from? What acid or base did it come from? And what did the acetate come from? So the positive always comes from a base. So what did Na positive, what did Na positive come from? It came from NaOH. NaOH was a strong base. So that makes Na a weak acid. So we can ignore the Na for sure. But the C2H3O2 must have come from HC2H3O2, which is acetic acid. Well, that's not one of our strong acids. It's a weak acid. And if it's a weak acid, that means that its conjugate must be a strong base. So C2H3O2 negative is an ion we would have to actually contend with. What would it do since it's a strong base? Bases like to accept. So C2H3O2 negative would like to accept an H positive from the H2O. The H2O would turn into OH negative. And if we have OH negatives around, is that acidic or basic? Right? That's basic. So this solution would be a basic solution. Okay? So this is the process of looking at a salt and determining whether the salt would actually be acidic or basic, or in some cases neutral, by looking at what it came from. Right? And of course, salts from strong acids and strong bases do not hydrolyze. They do not affect the pH at all, kind of like the NaCl example that I have at the top of this. Related to that, then, is this idea of a buffer. And this is probably something that you've heard about before you got into chapter 19. You've probably heard of a buffer before. A buffer is a solution that resists changes in pH. So if you were to add a little bit of acid or a base to a buffer, the pH wouldn't change. Unlike most other solutions, they would definitely change when you add an acid or a base to them. So how is that possible? Well, a buffer is made up of two things. It's made up of a weak acid and its conjugate base. Or you could, if you wanted to, make it up from a weak base and its conjugate acid. So, example. Let's take a weak acid like HF. And let's take its conjugate, which would be the F negative. Now notice I put an extra ion with the F negative. I put NaF. But remember, Na comes from NaOH, so we can ignore the Na. It's just there so that it is a salt. It has two ions to it. So if I take some HF, I know that HF, when I put it into water, will split into H positives and F negatives. It's acidic, but not really acidic because it's a weak acid. If I put NaF into water, F negative, remember, is the strong conjugate base of HF. So F negative, when you put it into water, wants to accept some of those H's back and produces OH negatives. So notice that this solution now has two parts to it. This solution has some H positives in it and some OH negatives in it. Now, what if I were to take and add some more acid to this? Let's say that I were to take some HCl and throw it into the solution. Well, the HCl is going to have some H positives that are going to suddenly change the pH balance. But no, these OH negatives will be able to go in and attack those H positives that are added and turn them into water, which doesn't affect the pH at all. What if I were to add some NaOH to this solution? Suddenly all those OH negatives should increase the pH, but no, the H positives are there to neutralize those OH negatives that might be added. So a buffer has two weapons that it can fight extra H positives or OH negatives that were to come in, right? It has two parts to it. So if you were to add an acid, the F negative would react with them and neutralize them, right? Actually, it's the OH negative from the F negative. And if you were to add a base, then the HF, the actual H positives from the HF, react with them and neutralize them. Now, you could add so much extra acid or base to a buffer solution that you use up all of the H positives or OH negatives that it has in reserve to fight it, and that means you've reached the buffer capacity. And by the way, buffers are really important to you because right now you have a buffer system in your body regulating your pH. All right, your blood in your body is just slightly basic. I mean, just slightly, a little over 7. But it has to stay there. If you suddenly went and decided you were going to eat a whole bunch of oranges, which have a really low pH because they're all acidic, right? Citric acid in the oranges, your blood eventually would turn acidic. It would ruin your body's chemistry and you would eventually die. You think, well, I know I've eaten oranges before and not died, so how does that work? Well, your kidneys actually have a buffer system built in where they can regulate the amount of H positives and OH negatives that are in your bloodstream, no matter what you eat. Now, is it possible that you could overcome the buffer system of your body? Yes. Is it also possible that your kidneys could malfunction and you could not keep the pH balance in your body? Your buffer system would break down? Yes, that's also possible. Right? But in most healthy cases, your blood is going to continue to stay at the same pH no matter what because it has that buffer system built in. By the way, that's what the whole point of urine is, right? That's why your kidneys produce urine, is because they're trying to regulate the pH of your body. All right, that's it. Hope that if you have any questions, that you're writing me, right? And we'll eventually get ready for the test next week. See you later.